All right, today we're going to look at complex numbers. And complex numbers start with the square root of -1 is 1i, or just I, we say. And we get that from the idea of square roots with negatives. Let me take you back to this for a moment, just to familiarize yourself with this. If I asked you what the square root of 49 was, hopefully you would say 7. And it's 7 because 7 times 7 equals the 49. In other words, two of those same numbers multiplied give you that. Well, if I ask you for the square root of -49, you might be inclined to say it's -7. And is that because -7 times -7 makes -49? No, it doesn't. Okay, so the number you think it is, it has to multiply by itself twice to give you back that number under the radical. It's going to give you a positive 49 if you use -7. So the square root of -49 is not -7. We say it's 7i. It's an imaginary 7. Now, if that doesn't make any sense to you, don't panic. Imaginary numbers have applications in electronics, okay? So this is useful in the real world. All right, but let's just build a little speed here to get you caught up on what you would have for answers like this. If I ask for the square root of -64, you would hopefully say it's 8i. If I ask for the square root of 81, be careful, it's just simply 9. But if I ask for the square root of -81, it's 9i. It's an imaginary 9. Now, that being said, if you were to take two numbers, here's another note you might want to write down. I squared is equal to -1. If that seems confusing, well, let's look at it like this. If I was to ask you, what's the square root of 25 times the square root of 25? Some people right away say, well, it's 25. And that's because the square root of 25 is a 5. Another square root of 25 is another 5. You're multiplying them, so it gives you 25. What's the square root of 81 times another square root of 81? Well, it's just 81. But that's because square root of 81 is 9. Another square root of 81 is 9. Two 9s will make the 81. So with that kind of reasoning, what if I had the square root of -1 times the square root of -1? Well, it's going to be -1. It's always that same number that's under the radical, okay? The same number under the radical, if you multiply it twice, you get that number. But here's another reason. The square root of -1 is I. The square root of -1 is I. Two i's is I squared. So the reasoning of -1 and using the I squareds tells you that I squared is the same thing, you see, as -1. So we got that fact written down. We got that fact written down, and we're going to use these in future lessons. All right, now, the property of square roots with multiplication allows you to say the square root of a number times another is just to multiply those numbers together and find their square root. So here's an example. The square root of 100 is the same as the square root of 4 times the square root of 25. You can multiply 4 and 25 and get the 100. And the square root of 100 we know is 10. Square root of 4 we know is 2. Square root of 25 we know is 5. So 2 times 5 makes the 10. It checks out. So how would you deal with something like this, the square root of -5? Uh-oh. Well, you can break it up, so to speak, or turn it into a multiplication problem of radical -1 times radical 5. Just like my 100 can be broken up into 4 and 25. But what do we know about the square root of -1? Well, hopefully you wrote down that it's I and then times radical 5. So you simplify that like that right there. Now, here's some practice problems. If you want to pause the video right now and see if you can figure out these answers, go ahead. Okay, hopefully what you did was break this into -1 times radical 3. That gives you I radical 3. Break this into -1 square root times radical a. That gives you I radical a. Break this into negative 1 times radical 36. That gives you I times 6. But be careful. You don't write I times 6. You write 6I. If you got a radical, you put the I first. Put the I first if you got a radical. By the way, that symbol is called a radical. I've been saying radical, and you might not have known what I was talking about. The square root symbol or the root symbol is the same thing as a radical. So if the radical is part of the answer and I is part of the answer there, put the I first. But if this is a whole number, or so if it's a whole number or an integer, you can put that number first, like you do your coefficients, okay, in front of your unknowns. All right, simplifying complex numbers. Now, we're going to simplify the square root of negative 50. So let's break it up first into negative 1 radical. And now let's think a minute. Perfect squares. Perfect squares are 0 because 0 times 0 is 0. 1 because 1 times 1 is 1. 4 because 2 times 2 is 4. 3 times 3, 4 times 4, 5 times 5, etc., etc. Is there a perfect square that will multiply and make 50? Yes. 25 and then 2. So if you break the 50 into the negative radical 1, the 25 and the 2, you can say I times 5 times radical 2, which simplifies to 5I radical 2. All right, see if you can do that with these two right here. Think about perfect squares. Pause the video if you want to try on your own. Okay, I would have said negative 1 and broke this up into 9 times 2. Then I would have had I times 3 times radical 2. Final answer, 3I radical 2. On this one, I would have said radical negative 1 times 36, radical 36 times 2, because 36 is a perfect square, and 36 times 2 makes 72. Okay, so that's I times 6 radical 2, or 6I radical 2. Now, some of you might be saying, well, I didn't know that 36 times 2 was 72. I don't have my 36s memorized. You know, you memorize your times tables, usually up to 12. So you probably knew that 9 times 2 made 18. No problem with that. But we don't normally memorize 36 times 2 making 72. So how are you going to get that answer if you didn't know that? Well, there's a couple of ways. One way you could do is like this. The answer we know is 6I radical 2. We could have said 8 times 9. After all, most people know 8 times 9 is 72. So then we could say I times, 4 times 2. 8 is 4 times 2, and then radical 9. Oh, so we got I times 2, square root of 4, times radical 2, times 3, square root of 9, and look what we have. I times 2 times 3, well, that's I times 6 times radical 2, which is 6I radical 2. Now, the last way to get these, if you don't know, is called the prime factorization. And we're going to work on that in a future lesson, but it always works as well. 72. Your prime numbers, this is the prime factorizations, 2, 3, 5, 7, 11, 13, 17, etc. You normally don't have to go past 7. But here's how the prime factorization method works. It works like this. You divide 72 by the first prime number, which is 2. It'll go in 36 times. By the way, maybe that would tell you right away to use 36 times 2. But if you didn't know that, divide by 2 again, and 2 goes into 36 18 times. Divide by 2 again, and 2 goes into 18 9 times. Now, when you get to 9, you can't divide by 2 anymore. So you try the next prime, 3. 3 will go into 9 3 times. And because 3 is a prime number, we don't divide anymore. There's no more division because now you've got a prime number at the top. But what all this means is 2 times 2 is 4. 4 times 2 is 8. 8 times 3 is 24. 24 times 3 is the 72. In other words, 72 is the same as 2 times 2 times 2 times 3 times 3. Therefore, I can say this. There's my negative 1. How about picking out 2 2s? That's going to be 4. How about picking out 2 3s? That's going to be 9. How How about keeping the last 2 by itself? So in other words, there's 4 times 9 times 2. There's the 36 we were talking about. Or it's I times 2 times 3 times radical 2. Square roots right there. So there's still I times 6 times radical 2, which is 6I radical 2. I know that's a longer way, but unless you know your times tables backwards and forwards, as in you just automatically know 36 times 2 is 72, you're not going to always be successful. So it might take a little longer, but that's all right. Okay, a complex number is when you write the number in the form of a plus bi. Now in this case, a is 5 down here in my example, and b is 7, okay? My note up here says they are always written in standard form with the real part first. That's a real number. A real number is just anything that's not imaginary. And then the imaginary part is second. Now let me ask you, what would we have if b right here was 0? And when I say b, I mean my 7. What if the 7 was a 0 all of a sudden? Well, you would have 5 plus 0i, and you would just have 5, which is a real number. Okay, no problem there. What if a was 0? Okay, what if up here I had, instead of that 5, see, 5 is the a number. You know, it's the a plus bi. Well, what if that was a big 0 plus the 7i? Well, you would just have 7i for your answer, which is called a pure imaginary number. So just a little trivia there for you. It's not anything I'm going to test you on, but just keep in mind that you do have a complex number even when b is 0, even when a is 0. Okay, you have the imaginary part, or you might just have the real part only. Adding and subtracting complex numbers is very simple because it's just like having an x right there or an a right there. It's just basically combining like terms. So this is just 4 plus 3i. And then when you add with a parenthesis, the parentheses disappear, and a plus negative is just a minus 4, and then a plus 3i. It just stays the same. The signs don't change, okay, when you add. So now we just combine like terms. 4 minus 4 is 0, and 3i plus 3i is a total of 6i. Now we don't need the 0 part. The answer is just a pure imaginary number, okay? It's 6i. When you subtract, the same idea. Okay, you're going to have 5 minus 3i, but the negative is going to change the signs, okay? You're subtracting negative 2, so you have positive 2. You're subtracting positive 4i, so you have negative 4i. Combined like terms, you got 5 plus 2 is 7. Negative 3i minus 4i is negative 7i. Now on this little screen I always have, is the final answer written in standard form? Real part followed by the imaginary part. Yes, real part is the 7. Imaginary part is the 7i, negative 7i. Imaginary, there we go. All right, in other words, you don't write this. You don't write negative 7i and then plus 7. Your numbers are correct, but your form has to have the 7 followed by the negative 7i. So don't write it that way. That's not the standard form up there. Okay. All right. Pause the video if you want to try these on your own. Okay, you should have said 7 minus 2i. The plus is not going to change the sign, so minus 3 plus i. That's going to give you 7 minus 3, 4, and negative 2i plus i is negative i. 7 minus 3, I'm just double checking. 7 minus 3i, well, what am I saying? What am I doing? See why I double check? I'm teaching you, and I still make mistakes. So you always double check. 7 minus 3 is 4. Negative 2i plus i is negative i. This one here, you're going to have 1 plus 5i, and then minus 3 and plus 2i. Minus 3 plus 2i. So 1 minus 3 is negative 2. 5i plus 2i is plus 7i. Okay, double check. 1 minus 3, negative 2, 5 minus plus 7. Okay, looks good. Is it written in standard form? Yes. Would it be wrong if you wrote 7i minus 2? I'll give you half off on a test if you write it that way because you did your math right. But it's half off because you didn't write negative 2 plus 7i. It's got to have the real part and the imaginary part second. Okay, so keep that in mind. Every year I test students, there's always 3 or 4 that want to put the imaginary part first. You don't do that. Real part first, imaginary part second. All right, now graphing complex numbers, this is the complex number plane. It's like a coordinate plane, but it's got complex numbers to graph. Notice the real numbers are on the x-axis. The imaginary numbers are on the y-axis. So if you want to graph 2 plus 3i, you simply go to 2. Let me write that bigger in case it's not showing up good. You go to the 2 on the x, you go to 3i on the y, and you put your little dot right there, okay? And that's how you graph 2 plus 3i. Now, this arrow is not necessary. It's just on there showing you that's where it ends up, 2 and 3i. All right, take a second, pause the video, and make a little graph of this and graph 3 minus 2i. Okay, you should have went to positive 3, and then negative 2i is down there. So your graph of 3 minus 2i should have been that right there. Again, you don't need the arrow. The arrow's just on there showing you where it ends up. It ends up right there in quadrant 1, 2, 3. It ends up in quadrant 4. Now, the absolute value of a complex number is the distance that the number is from the origin in the complex number plane. All right, so first of all, if we graph 3 minus 2i, we're back to where we were right there. And read this again, it's the distance that that number is from the origin. Well, the origin's right there at 0, 0. So you want the distance going down there. Once again, you don't even have to draw that line. It's just I'm trying to make a point that from there to there is going to be the absolute value of 3 minus 2i. It's that distance. Well, how do I figure out that distance? Do I take a ruler and measure it? No. You make yourself a right triangle and use the Pythagorean theorem. If I drop a line straight down, I've got a right angle there, okay? And now let's think a little bit. The c side in the Pythagorean theorem, a squared plus b squared equals c squared, the c side is always the hypotenuse. The longest side is the hypotenuse. The side across from the right angle is the hypotenuse, okay? Across from the right angle. After all, you might look at a right triangle sometime and say, I can't determine what's the longest side. They all look about the same. So it's always right across from the right angle. That's your hypotenuse. That's the c side. Okay, that being said, we know this distance here. After all, I went down to negative 2i, so it's a distance of 2. It's not a distance of 2i, okay? 2i is not a distance. It's just there's 2 units that you're going down to do that. By the way, you don't put negative 2 because a distance is not negative. So we wouldn't say the distance is negative 2. There's no negative distance. If I walk backwards or forward, I'm still walking a distance I measure in positive numbers. Going across here, we know this distance is 3. 0 to 3. So we can say 2 squared plus 3 squared equals c squared. We can say we can say 4, 2 squared is 4, plus 9 equals c squared. We can say 13 equals c squared. And remember, when you get to c squared, you've got to apply the square root. You apply the square root to both sides so that c is equal to the square root of 13. You can leave it in radical form unless the directions tell you not to. Otherwise, you got to get a calculator to estimate the answer. I know I told you whenever you apply the square root, you have to put the plus or minus. However, in this case, you don't use the negative because, again, it's the distance, and there is no negative distance. So your absolute value, the distance from the origin to the complex number, is square root of 3. All right, pause the video and see if you can do 2 things. Can you plot negative 4 plus 3i on the complex plane and then determine its absolute value? Okay, you should have went here to negative 4 on the x-axis, which we call the real axis, but it's on the x that you're familiar with. And up to positive 3i on the y, or the imaginary axis, and line those up right about there, okay? There's your graph of negative 4 plus 3i. The absolute value is from here to the origin, okay? So let's go ahead and make ourselves a little right triangle, like this, with a right angle. And remember, this is the c side, so that's what we're finding. This distance, we went up to 3i, so that's got a distance of 3. This distance, we went back to negative 4, so it's got a distance of 4. Again, just think about this. If you're stepping backwards 4 spaces, I don't say you have a distance of negative 4 feet or something, okay? You walk backwards 4 feet. You didn't walk negative 4 feet. You still walked 4 feet. So distances are always positive. So we have a squared plus b squared equals c squared. We have 3 squared plus 4 squared equals c squared. We have 9 plus 16 equals c squared. We have 25 equals c squared. We take the square root, and the c value is 5. Of course, some of you might have known that because you know that when you have a 3, 4, 5 right triangle, and these sides are 3 and 4, this has to be 5, okay? All right, well, that's all we have for the complex number plane. The last part is figuring out complex solutions. So with this equation right here, remember, when you figure out solutions, it's always the x values that make y equal to 0. So replace y with 0 and figure out the x values that make y equal to 0. Any solution is always the x that makes y 0. So if you were given this right here, you would take away 81, obviously, and you would have negative 81 equals x squared. So you apply the square root to both sides, and you get x squared equals, positive or negative, because whenever you take the square root, you got to account for the positive and negative, 9i. That's what x is. I wrote x squared, should not have. So your two solutions, your complex solutions, are positive 9i and negative 9i. You might get this answer immediately, but if not, pause the video, work it out, and I'll be back. Okay, hopefully you replaced 0 with y. Hopefully you then said, well, I take away 144 from both sides to get x by itself. So negative 144 equals x squared. That's gone. Apply the square root to both sides, and x is equal to the square root of 144. Let's see, that's negative 1, that's 144. So that's going to be I times 12. But we got to account for the plus and the minus here. So if you got a final answer of plus and minus 12i, you were successful. Copy down the homework and make it a great day. Hope everything is going well.